Okay, so we're doing the simple pendulum today. Now, in your classes, you're probably just given this equation for the period of a pendulum, right? With really no other description, like where it comes from. Period of pendulum. And we usually represent it with a capital T, the period. That's equal to 2 pi times the square root of L over G, where L is the length of the pendulum and G is the gravitational constant near the surface of the Earth. Okay. Well, not technically gravitational constant, the acceleration due to gravity, not the gravitational constant. But so that's the equation.
You're not showing us your work if that's what you're trying to do.
Oh, what the hell? Yeah, okay. Thanks for speaking up, because for some reason I thought it was, but I guess it disconnected or something. What the hell? All right, give me a second. That's funny. Okay. There we go. All right. Okay. So, so here we go. So lab 10, simple pendulum. The period of the pendulum is just t equals 2 pi square root of L over G, where L is the length of the pendulum and G is the acceleration due to gravity, 9.81 meters per second near the surface of the Earth. G can be something else if you're on a different planet, and oftentimes when you're doing these period of a pendulum problems, you'll be asked to, here's the period, here's the period, here's the length, what's the gravitational acceleration on the planet that we're on, or whatever it might be. And so, this is kind of how you would do it. You would solve for G here in case. But now, oftentimes you're just given this, and it's kind of a boring, they just give this to you and say use it. So I kind of took it upon myself to do like a little derivation, but I guess there's some derivation in the labs, it turns out too. Mine will be like slightly different than that. I'm just going to give you a derivation of this just so you can see it. Some of you may know what a differential equation is. Some may not. You might have all at least some point seen torques. So I'm going to basically just make an argument on what this actually is based on torque. Now, the other thing to remember before I kind of get into this is that period is also 2 pi over omega, or 1 over the frequency. This is another way to look at your period, right? Just 1 over your frequency. Your frequency is in cycles per second, so periods is in seconds. I can go ahead and write the units for that too. Period is seconds per cycle, and frequency is 1 over that, so that's cycles per second. Okay. Omega, that omega there is your angular frequency. That's another way to interpret the frequency of this thing is through radians per second, which would basically be how much of an angle does it swing through per unit of time as this thing oscillates. So here we go. Drawing the actual pendulum itself, draw it like this, kind of exaggerated amplitude. This will be our theta right here. What I can do is I can break this thing down into components. Like right now we know that mg is facing straight down. That's going to be our mass times gravity. That's the weight of the pendulum's weight, the weight on the end of the pendulum, called the pendulum bob. The thing is, we're in a reference frame right now that's the usual lab frame, which is that straight up is the y direction and to the right is the x direction. But I want to rotate into the frame that's along with the tension. So it's like my y direction would be along the tension of the string and my x direction would be like this. I want to rotate into a different frame here. And the reason I would do this is because I actually want the force component that's perpendicular to the string itself that's trying to pull it back down, right? Because that component right there of mg, that component of the weight, is actually the one that's restoring this thing back down to its equilibrium position, which is straight down. And the restoring force is the thing that's usually the one that we actually want to see for any kind of oscillator. And so what I would do here is I would draw a line straight out. This would be my opposing the tension component, and then I'd have a component going straight down like that at 90 degrees to each other, where my hypotenuse is mg. That's the hypotenuse right here, mg. What I want to do is I want to first show that the angle inside of here is something we do know. If we know the angle of the top, which is theta up here, if we know that angle, then it turns out that this angle right here is also theta, and that's because this line is parallel to this line, and this line is parallel to this line. So you can see that the angle between like the double dash and single dash is theta, and we have another double dash, single dash down there, so that's also got to be theta. You can also think of it as a, if I continue this line up here, you'd see that it's an alternate interior angles, then also vertical angles problem, right? Where that's theta, that means that this is theta as well, alternate interior angles, and then because of vertical angles, that means that this angle down here is also theta inside my MG triangle. Okay, but that's a little much information there, but there you go. So this triangle, if I did some right triangle trig there, I'd find that sine of theta is equal to opposite over adjacent. So that's going to be this side here. I'll call, I don't know, I'll just call it like F restoring. So it's going to be the side F restoring over the mg. So the restoring force in this case is equal to mg sine theta. Okay. Now here's the deal. This pendulum is we're gonna describe it through rotational dynamics rather than linear dynamics. So rather than looking at F equals ma, we're going to look at torque equals the sum of all your torques. So torque is equal to I guess let's call it force times radius, and that's also equal to I alpha. So some of you may have seen this at some point, especially if you took like an AP physics in high school, or I mean a lot of other physics classes. And you've probably seen this semester. I'm hoping maybe a little bit. Now, torque is actually, just to be like completely clear, torque is really the force crossed with the radius. So torque is a cross product of force and radius, which can be represented as Fr sine theta. I'm going to call it phi, so I don't have the same thetas up there, where phi is the angle between your force and your radius. And so if they're at 90 degrees to each other, right? So, you know, if your angle between the two vectors is 90, then you can see sine of 90 is just 1, and you just get the force times radius. Okay, but technically it's a cross product. So you got to be careful about that. If you ever have the force not exactly perpendicular to your radius, in this case, the radius is actually the length pendulum, which is L. So we're actually going to represent this as I alpha equals the force times radius. Radius is actually L, so it's going to be L times mg sine theta. Okay. Now, the rotational inertia, that's what I is. And I for a pendulum is really just, we're assuming it's a massless string with a mass on the end. And whenever you do that, you just say it's the mass times the length or times the radius squared. In this case, the radius is L, so it's going to be mass times length squared for this system. And this is just for any system that has a mass on the end of a weightless string. So that's going to be ml squared alpha equals L mg sine theta. Another thing is, what we do to make this simpler is we say, well, we're going to do this system, we're going to look at the system for very small oscillations. So we're going to have our angle theta just move just barely a little. Again, when your theta is small, when theta is much less than 1, you can say that sine of theta is roughly just theta. Okay, and that's kind of weird, but if you put your calculator in radian mode and you go ahead and just calculate like what's sine of 0.01, you basically get 0.01, right? So that's that small. This is called the small angle approximation right here. And so what we'll do is we apply that. And here's the other thing. Alpha, now remember that your second derivative of your position is your acceleration. So we're like x double prime of t is equal to a of t. Remember that stuff? Well, same thing works with alpha. Alpha is your second derivative of your position, your angular position, right? Your theta, actually, in this case. So it's actually your second derivative of your theta with respect to time. And another way to write that is to write theta double dot, those two little dots above it. That just means second derivative, okay? So then if I substitute those things in here, I'd get ml squared theta second derivative equals lmg theta, okay? Cool. So this right here is a differential equation. We have on one side the second derivative. It's a second order differential equation. We have the second derivative on one side and we have the original function on the other. Okay, now if I divide both sides by the ml squared, I'll get that theta double dot is equal to, the m's cancel, I get g over L times theta. Okay, I'm actually gonna go ahead and go back up here and call this force negative. just as a convenience, just for convenience sake. You'll see why. So this is my differential equation right here, okay? Now, why is that useful to us? I'm gonna go to the next page here and show you kind of what physics people do. So we have this is equal to negative g over L times theta. Now, theta is a function of time, okay? And what I'm gonna do is I'm gonna guess what f of t is. Okay, now, the thing is, we have some function. Now, this is a guess, but there's also other ways to do this. If you took a differential equations class, this would be solving a second order differential equation. I think I forget the method you want to use here, but whatever. We're not going to do that right now. This is going to be what's called an ansatz. So I'm going to teach you a little trick, little term here. An ansatz is an educated guess. I guess it's a super educated guess because I could have said educated guess, but I said ansatz. So there you go. It's a classy educated guess. So the thing I'm going to guess here is like, okay, I have some function, theta, with f of t. If I take its derivative twice, I get back the original function, but with a negative and a constant in front. What do we know? What functions do we know do that? Well, there's only a few functions that are cyclic like that, and that's sine, cosine, and e, right? E to the x or whatever. In this case, because the negative's there, I'm going to pick cosine, either cosine or sine. I'm going to pick cosine because cosine starts at a max amplitude. When you put in a 0 for cosine, you put a 0 inside your cosine, you get 1, so you can start at your max amplitude. So I'm going to guess that theta is actually just cosine of omega t. Now, technically, there'd be an a cosine omega t to represent the amplitude, but I'm just going to assume amplitude's 1. I mean, I guess to make it more rigorous, I could say something like it'd be a cosine omega t. And let's just assume a equals 1 for simplicity. Okay. So we're going to have this theta is equal to cosine of omega t. Now, theta dot, which is the derivative, is going to be negative omega sine omega t. Okay, do my chain rule there, taking the derivative of my cosine. Negative pops out. Theta double dot is negative omega squared cosine omega t. Okay, if my cosine omega t was my theta, right? If theta is equal to cosine omega t, then what I've just generated was theta double dot is equal to negative omega squared theta. Which, hey, that looks like this, doesn't it? Okay, well, that means that my omega squared must be equal to g over L. In any case, if I solve this for omega, my omega must be equal to the square root of g over L. Okay, and the omega, since it's up against the t in my cosine, it basically dictates how fast this cosine changes as a function of time, right? If it's a large omega in there, then when I plug in a time, it gets multiplied by some huge number, and then I get a huge angle for my cosine input. So it's going to cycle through the circle really fast. If my omega is just 1, then it cycles through at the regular rate. If it's a half, then it cycles through slower. So essentially, that omega is my angular frequency. It's telling me how fast I'm cycling through, okay? It's speed times time. It gives me, speed times time is your distance. In this case, theta is just omega times t. So that's why the omega t is in there instead of a theta, right? Essentially, but I don't want you, because theta I'm writing is a function here, so I'm not trying to write, but I'm just saying the angle you go through is omega t. So maybe I'll just write like angle equal omega t, but let's not worry about that for now. But what I wanted to show you here was this is essentially how you got omega is a square root of k over m for a spring, right? What you do is you start with Hooke's law. You start with f equals negative kx, and you say f is, well, that's equal to m times my second derivative of my position. And then it's the same exact song and dance. You have the second derivative on one side, you have a single derivative, or you have the original function on the other side. You guess that a cosine will work. Turns out that the omega that's in there will actually become the square root of k over m, just like this one became the square root of g over L. Okay, so that's where all this stuff comes from. Just so you've seen it at least once. I don't know if you did this in your class, but you'll eventually do this if you continue on and do higher level stuff. So there it is. Good to see. Now we know that the period of anything is just 1 over the frequency, and we know that the frequency is we know that omega is actually just 2 pi times the frequency. Since frequency is 1 over seconds, you multiply it by a cycle. It's like the frequency is a cycle per second. You multiply it by a cycle in radians, which is 360 degrees, which is 2 pi, and then you get radians per second. So combine those two things together, and what do you have? Well, you've got t equals 2 pi square root L over G, because you flip it over because it's the omegas on the bottom there with the F. Okay. You also can write this as, t equals 2 pi over omega. Okay, that's where it comes from. Cool. So, all right. So basically for this lab, hopefully you guys have it pulled open here. At least you have a few pulled open. I can go ahead and share that screen too. And I'll have to come back to this because they give you some kind of weird questions I want to go over. So here we are. Now, okay, so check this out. So for the first part here, what you basically did was, if you were in the lab, you would have changed the length of the pendulum a whole bunch of times, and you would have observed 15 cycles, timed how much time it took to go 15 cycles, and then found the period. Now, how are you going to find the period? You're not going to use the period equation. Right here, you have the time of 15 cycles. So you take this number and divide it by this number, and you get this number, right? Because that's how long it takes to do 15 cycles. Divide by 15, that's how much time it took to do one cycle, right? So you're not actually using the equation here with L and all that. You're actually just calculating it with these two rows, these two columns divided, each one of these, okay? That's what you're doing here. Same thing here for all of these, for these tables, A1, B1, and C1. That's all you're doing. You're taking the time divided by cycles to get period, okay? And then you're just gonna answer some questions based on the observations of those plots, or those tables, which is basically like, what happens to the period as you adjust the length? So you'll notice that the period changes as the length changes. Does it get smaller when the length goes down, or does it get larger when the length goes down? Just go ahead and answer that question. That's all I want you to see. This next one here, you're going to actually use that equation, but you're going to use this one here, this G equals 4 pi squared times L over T squared. That's just, what that is just the period equation, but solved for G instead. So you just square both sides and then move the G over and move the T on there, and that's about it. Now what you're going to do is you're going to use the corresponding period that went with 0.7 length from table A1 up here. You're going to take this period, you're going to plug it into that equation for T, and then you're going to use this for L, and then you calculate G, okay? And you're going to do that for each one of these using the corresponding period. And you should notice, it asks you right here what you observe, you should notice that they're all about the same. I mean, there's going to be some experimental error, but they should all be roughly the same, okay? So, now part B here says period of oscillation is a function of amplitude. What happens when you change the amplitude? Well, the equation is just, go back up here, the equation is just, this one right here. It's 2 pi squared L over G, right? So there's no A in there, right? There's no A, there's no M, there's no amplitude dependence, there's no mass dependence. So you should expect nothing to change when you change the amplitude. The amplitude is just how far you swung it. Okay, so you bring it out to here and let go, or you bring it way out to here and let go. It shouldn't really affect it as long as you're within like a small angle. And that's we're not gonna disobey the small angle rule here. So what happens in the period as you adjust the amplitude? Nothing. Should be nothing. So verify that you have nothing. Period of oscillation is a function of mass. Should be nothing, right? Shouldn't change at all. Okay, calculate the angle, the amplitude. So this is something I'll do really quick. Okay, I'm going to leave it off here and go back to the actual sharing of the notes. Okay, come on. Okay. So for part of it here, we have, for part C, number 2, it's asking, so, the amplitude of the pendulum's oscillation is usually measured by the angle through which it swings, not its horizontal displacement. And that's because it's a lot easier to measure the angle instead of the horizontal displacement. And that's what we did for the ballistic pendulum lab. This is the angle that it swings through. Let me draw it super exaggerated over here. And the amplitude is actually this value here. That's the amplitude. Okay, and this is the length. That's 90. They're asking you basically, well, for some given amplitude, what is the actual theta? Like, what is my actual angle there? So the deal is, well, technically, this is the amplitude. It's not the actual. It's not the distance traveled. Right? Distance travel is an arc, and so you have to do an arc length formula. But we're not going to do that here. We're just going to say that's the amplitude. So what I would do here is actually just some simple right triangle trig. I would say sine of theta is going to be opposite, which is a over the length, which would then mean that my sine inverse of the amplitude over the length is going to give me my theta, right? So theta for the example that they give us is the sine inverse of, and they say the amplitude for this case is 6 centimeters, so that's 0.06 meters. And they say the length is 60 centimeters, so that's 0.6 meters. And if you do that right there, let's go do it for you. I might as well right here, right? We'll put it in degree mode just so I get degrees instead. Inverse sine of 0.06 divided by 0.6 is, I've got 5.74 degrees, which is pretty damn small. What's sine of 5.74? It's 0.1. But if you plug in if you convert 5.74 degrees to radians, and you plug that into your sine, you're going to get about the same answer. So this is an example of the small angle approximation. Basically, I just wanted to show you here. So, if you have degrees, you multiply it by pi over 180, right? So you do 5.74 degrees times pi over 180. That gives you 0.1002, basically. Okay, and guess what? What's sine of 0.1002? We'll plug that in right now. Sine of 0.1002 is 0. Wait. What do I do here? Oh, I'm in degree mode still. Okay, let's think, what the hell? Sine of 0.1002 is 0.100. Okay, so it's basically the same as theta itself, right? It's approximately the same. That's just an example of the small angle approximation here. Anyway, so part 3 here says the period of pendulum is independent of amplitude only if the angle is small. Was this the case? Basically, they're saying, hey, was my period independent of amplitude? Okay, well, for a period to be independent of amplitude, it needs to be a small angle approximation. So if my period was independent of amplitude, then I must have had a small angle approximation valid here, right? And then you're going to see that it was. You should see that it was. The conclusion here, which variables affect the period of motion of the simple pendulum and which do not? Well, we look at the equation for period is t equals 2 pi square root L over G. There is no M, there is no A, so only L and G actually affect it. Okay, questions. Right here, question section. Question 1. It says, must the spring obey Hooke's law in order to oscillate? So this one, if you want to argue that like you can make it oscillate through some other means, I guess I'll accept that. The Hooke's law is this F equals negative kx thing, right? F is equal to negative kx. That's for a spring. Now, this causes oscillatory motion because if I draw out this mass, let's make this x equals 0 right here. And let's make my mass over here. Well, if that's x equals 0, this is the positive x region. This is the negative x region. If I plug in a positive x into that equation, I'll get a negative force, which means it's going to point to the left. Okay, and if I'm over here and I plug in a negative x to this equation with the negative inside with the k, I'll get a positive force that'll point to the right. So this force always points towards x equals 0, and we always make x equals 0 the equilibrium, okay? X equals 0 is the equilibrium. That means that the force, which is the force of spring here, is a restoring force. Okay, so it's always pointing towards equilibrium. So the thing is, really what we need is a restoring force. Now, does it have to be Hooke's law? I mean, the pendulum isn't Hooke's law, but it's talking about a spring. And a spring does obey Hooke's law. So it's kind of like, must a spring obey Hooke's law? Well, yes, because this is the real world and that's how physics works. So, yes, the answer is basically just yes, it does. Okay. The main condition though is really it needs a restoring force. Okay. All right. So, question 2 here. When a body's oscillating some part of motion, where is its acceleration equal to 0, if it even is? Well, we know that force is equal to negative kx, right? So let's plug in what happens when x is equal to 0, right? So like, what's f of 0? Well, um, when x equals 0, so you're at equilibrium, your force equals 0, right? Your force is also equal to mass times acceleration. So if your force is equal to 0, your net force acting on the object is 0, then so is your acceleration, okay? So basically, that's something you always find out. Whenever you're trying to find where your acceleration is equal to 0, find where your force is 0. Because you usually have an equation that tells you where your force is at any point. F is 0 means that is equal to ma. That means that acceleration equals 0. So you see acceleration equals 0 at x equals 0, right? Which means acceleration equals 0 at the equilibrium. Okay. So there it is. When it's passing through the equilibrium point, the force is reduced to 0 for a second, and the acceleration is 0 in there. But the thing's still now it's got maximum velocity, and it's going to start moving past that, and that's when the force starts pushing the opposite direction, which means you're decelerating. That the acceleration is now positive when you're on the left side and negative when you're on the right side. So it's always trying to accelerate you back. Question 3. Trying to build a metronome using some pendulum. Assume the pendulum bob weighs 1 kilogram, g is 9.8 meters per second squared. How long should you make the pendulum arm so that the metronome ticks with a frequency of 100 beats per minute? Let's just go to the next page here so I can make sure I don't run out of room. So, Q3. Okay. We have this equation for period, right? We have t equals 2 pi square root L over G. And they gave us the frequency. They gave us the frequency is 100 beats per minute, right? And we know also that the period is 1 over the frequency. So essentially, we got to take frequency, go to period, and then relate period to L, and then find out what L needs to be. Okay, it's pretty straightforward, but a little bit of algebra here, so I'll just go ahead and kind of work through it. One thing I want to talk about is the beats per minute. That's basically, a beat is what? It's like a cycle, right? So it's 100 cycles per minute. Okay, and what I actually want is cycles per second, and then I want to turn that into seconds per cycle for the period. So what I'm going to do is I'm going to multiply this by minutes on the top and seconds on the bottom. Okay, that'll cancel minutes. So I'm going to put 60 with the seconds, 1 with the minutes, and then I have 100 over 60. 100 over 60, and that's going to be basically 1 over seconds, cycles per second. It's like, kind of like 1 over seconds. That's my frequency. If that's my frequency, and t is 1 over frequency, then my period, is actually 60 over 100, which is 0.6 seconds. So that's my period, okay? So I can take this equation for t, and I can square both sides. I'll get t squared equals 4 pi squared times L over G. I can move the G up with the T, move the 4 pi squared down to the bottom, so I'd have T squared G over 4 pi squared equals L, right? And then all I have to do is throw in that period there, 0.6 squared times 9.81 over 4 pi squared, and then my L is equal to whatever that is, and I'll just go ahead and you can do that. Okay. Question 4. What is the frequency of a pendulum whose normal period is t when it's in an elevator in free fall? Okay, when you're in free fall, you feel something. The thing that you feel starts with a W, and you feel it is weightless. That means to you, in your inertial frame, which is inside the elevator where you don't have any frame of reference outside seeing something else move, you're stationary, or seeing the fact that you're actually moving. it looks like you're not accelerating, right? Inside the elevator, you know you're falling to the ground, but assume you don't know that. You're just in some elevator and you're in space. Let's just say, you're just in a box in space and you feel weightless. Do you know if you're accelerating or not? The thing is, if you feel weightless, you're definitely not accelerating. If you're accelerating, you'll feel like pushed to the back because, well, essentially, the elevator wants to go that way, and then you want to stay stationary, so you'll get pushed to the back of the elevator, right? If you're in space, this is a great example. But um, in a falling elevator, when you're falling with the elevator, both falling at the same rate, you're going to feel weightless in there. You're just going to be like floating, right? And that weightlessness means that you feel like g is equal to 0. Okay. Now, period is 2 pi square root L over G. So if I plug in G equals 0, I divide by 0, I get T is undefined, right? Which is basically saying that it doesn't exist. It's not infinity, it just doesn't exist. T is undefined. If I look at frequency, which is 1 over period, I'd get 1 over 2 pi square root of G over L. And if I plug in G equals 0, I get the frequency equals 0, which means it's 0 cycles every second. Okay? And that's your answer right there. So you can see that undefined period means there's no such thing as a seconds per cycle because there's no cycles happening. And that makes sense because the only way that pendulum actually swings back down, as I said earlier, as I showed in this math back here, was that it's actually dependent on your G value, right? So it's dependent on G. It's mg is the weight that's actually pulling you back down. But it's mg sine theta. Question 5, and the last question. We usually assume that the mass of the pendulum arm is negligible. It's not negligible. What does that do to the period of motion? So this is actually a pretty complicated question. I was going to go here. Question 5. Do this one. Q5. So it kind of we have to go back to the expression that I had earlier, which is that my I alpha was equal to my LMG theta. Remember, we're gonna do small angle approximations there, so it's not sine theta, it's just theta now. In fact, that's not even alpha, right? That's theta double dot. Let's go straight to that spot. We're leaving the I there for now because my I is different when I have a string with mass on it. Okay. Now the problem here is the system is going to be set up like this. It's going to be the total rotational inertia of a system that has a rod with, essentially it's not a string anymore. It's kind of like the rod problem. So you have something that's oscillating about that point, and you have some rod with a certain thickness and has a certain mass, and you have a mass on the end of it right here. Well, yeah, the rotational inertia you have here is going to be, so you're rotating around this spot right here. You're going to have the total rotational inertia is going to be the I of a rod about the end plus the I for your point mass. Assuming it's just a point mass, not a cylinder, not a ball or whatever, right? Now the equation here turns out for the rod about the end is 1/3. I'll call it big M for mass of the rod times its length squared. I believe it's 1/3. I should double check that. Yeah, it's a third. Plus, and then this will be the mass of the point mass times its distance from the axis, which is also L, and it's squared. Okay, so that's our new rotational inertia. If the rod itself has mass. Now I have to plug that into our expression. And you can see that this becomes, I can pull out the L squared, so it become L squared times, and this is basically M over 3 plus M times theta double dot is equal to LMG theta. I can divide over the L squared, and then I can do a common denominators here, so I'd get big M plus 3 little m over 3 is on this side here with my theta double dot. Divide the L squared over, and I'll get mg over L times theta. Divide that entire thing over there again, so now I'm going to have my theta double dot is equal to, let's see, I'll get 3 mg over L times big M plus 3 little m times theta. Okay, and this is supposed to be negative there, whatever. Keep not putting my negative in there. Okay, so what does that mean? That means my omega squared is now equal to this 3mg over L times m plus 3m thing. Okay, which means then that my omega is equal to the square root of that business. Okay, now what the hell does that mean? Is that bigger or smaller? Well, here's the thing. We know that this is like our new omega. Let's call this like omega 1 or something. We know that omega naught, the original omega, was just the square root of g over L. Okay, so what I can do is I can take out the square root of g over L here. I can write this as omega 1 equals this 3m over big M plus 3 little m inside of a square root times the square root of g over L. That's equivalent statement, right? Is pulled the g and the L out as separate square root. And you can see that now it's really just, this is omega 1 is equal to this business, the square root, times omega naught. Okay, so what I found here is that you can see that if m equals 0, right? Oops. Oh, God. What was that? Okay, there you go. If big M is equal to 0, omega 1 is equal to omega naught. Big M being the mass of the rod. So that's kind of obvious, right? We just, if we go back to saying, hey, this rod no longer has mass, then we're just back to the original angular frequency. Cool. However, if m is greater than 0, we're going to have that omega 1 is, let's see, if that big M is greater than 0, then this is not, so, okay, look, if m equals 0, we have 3m over 0 plus 3m. That's just 3m over 3m, which is just 1, and the square root of 1 is just 1, so I get omega 1 equals omega naught. Okay. If big M is something larger than 0, then the denominator of that 3m over big M plus 3m thing, the denominator is larger, which makes that number, the square root of that business, makes that number smaller. Because the denominator is larger, the number gets smaller, which means that's a fraction times omega naught, which means omega 1 is going to be less than omega naught in that case. So that's how we would do this kind of problem. This is how you would try to answer this question. Like if you had this on an exam, this is what you'd want to do. You'd want to go back to the actual derivation of the omega and rederive your new omega and then say, hey, okay, well, if my m equals 0, this is just 3m over 3m, it's just omega naught. If my m is greater than 0, you can see my denominator is larger here, and I'm actually going to have omega 1 being less than omega naught. Okay, so I don't know if they actually intended for this to be this complicated, but this is how you would have to do this problem. Anyway, so that just about does it. That concludes our last lecture for the semester right there. Wow. I'm going to